Hello everyone, welcome to Ask IITians and my name is Sanchit Gupta and this is the lecture number 4 of work, energy and power. So let's begin. In this lecture we are going to cover spring potential energy, power and commercial unit of energy. So these three topics we are going to cover: spring potential energy, power and commercial unit of energy. Oh, okay. Before discussing spring potential energy, let me tell you something about the spring force. So what is spring force? Let's see. If there is a spring which is connected to a mass, if I stretch it, let's suppose it is in normal position. If I stretch it a bit by a distance x, so it is going to apply force towards left. It is going to apply force towards left. Similarly, if I compress it, it is going to apply force towards right. So this is what is spring force. But how, on what factors does it depends? The amount of stretch that we have given to it. So in this case, the amount of stretch that we have given to it is x, or maybe the amount of compression we have given to it is x. So the force of the spring is actually proportional to x, and it comes out to be k into x. When we just remove the proportionality sign, we introduce a constant. So this is the force, and when we stretch a spring, the spring will pull towards it, and when we compress the spring, then its spring will push the block away from it. So that is what a spring force. So guys, and it is written also here that spring force is directly proportional to the compression or elongation caused in it. Okay, so let us move ahead to the next slide. Okay, now comes what is spring potential energy. Spring potential energy, guys, is nothing but work done to quasi-statically stretch or compress the spring. What does it mean? What does it mean quasi-statically stretch or compress the spring? Yeah, it is shown that if a spring is there which is connected to a block, and it means quasi-statically stretch or compress means that we are stretching it very slowly. We are stretching it very slowly to a distance, to a stretch x. Very slowing, we are just stretching it. That doesn't mean, that is meant by quasi-statically. So when we stretch it to a distance, to a elongation x, so the in that case the elastic potential energy stored in it is equal to half kx square. That is the formula of a spring, elastic potential energy of a spring. And what is this? It is the energy stored uh, by doing work done, because whatever work we are doing on this system by stretching it, that is getting converted to elastic potential energy of the spring. So the formula of it is half kx square. Okay, so let's move to some questions. Here it is written that 2 kg mass is attached to a spring on a horizontal surface. If the elongation is 4 centimeter, determine the elastic potential energy of spring. So here we know that elastic potential energy is equal to half kx square. This is the elastic potential energy, and it is given that elongation is 4 centimeter. Elongation is 4 centimeter. Okay, so we can know that half let's suppose k of the spring is 100 Newton per meter. So and the elongation is given to be 4 centimeter, so it will be 4 centimeter, because the SI unit of elongation is meter, so 4 centimeter would be equal to 4 into 10 to the power minus 2 meter. Okay, so it will be 4 into 10 to the power minus 2 square. Okay, so it will be half k. Let's suppose k is 100. And x square is x we have put, and in place of x we have put 4 into 10 to the power minus 2. So it will become 16 into 10 to the power minus 4, and we cut it, so it will become 8 into 10 to the power minus 2, means this much joule. So this is the elastic potential energy of the spring. Okay, so we have just applied the formula half kx square, where x is the elongation or compression in the spring. If the spring is elongated, then also the spring potential energy is this half kx square. If the spring is compressed, then also the spring potential energy is half kx square, where x is the elongation or compression caused in the spring. Okay, so next is given elongation of the spring stretched by a force is 10 centimeter. What is the potential energy of the elongation of the spring if the elongation is 20 centimeter? This we have to calculate. So first it is given that when force is 50 Newton, we know that force is equal to k into x. Okay, guys. So it is given that when force is 50 Newton, the elongation is 10 centimeter. So let us just put the values. Force is 50 Newton and elongation is 10 centimeter, means 10. And again, we have to convert the centimeter into meter. So it will be 10 into 10 to the power minus 2 meter. Okay. So here, how much k is coming? This 1 and 0 cut down, and it is coming out to be 500 Newton per meter. So k comes out to be this, and we have to calculate the potential energy when the elongation of the spring is 20 centimeter. So it will be half k is 500 into x square, because we know the formula of the elastic potential energy is half kx square. So it will be half k into 20 square. So it will be half k into 20 into 10 to the power minus 2, because we have to convert 20 centimeter into meter. So it will be this half into 500 into 20 into 10 to the power minus 2 means 0.2. So 0.2, the square of 0.2 is 0.04. So it will be 0.02, and these 2 and point gets cancelled out. So it has become 10. So the elastic potential energy is coming out to be 10 joule. Okay, so let us move to next question. A block of mass m is hanging from the ceiling with a spring constant in its natural length. What is the speed of the block when it attains equilibrium? So what it is given that initially the block is hanging like this and the spring is in natural position. So because of the weight of the block will go down, and when it comes into its equilibrium position, then we have to calculate the potential speed of the block. Let's suppose it has come to its equilibrium position by moving a distance x. So because it is in equilibrium position, so what are the forces? The net force acting on this block would be equal to 0. So what are the forces acting on it? Mg is downwards and spring would be stretching it towards upwards. So this would be the force acting on it. So we can say from this condition that mg would be equal to kx at equilibrium position. So here what is x coming out to be? Mg by k. Okay, so now we have to calculate the speed, velocity at this equilibrium position, because when it is moving downwards, it will attain some velocity, and at the equilibrium point, it will be having some velocity. So here, let us apply the work energy theorem. So here work done by gravity. We can assume that work done mg is applying, mg is acting downwards. So work done by gravity, or we can apply work energy theorem. So means work done by all the forces is equal to change in kinetic energy. This is our work energy theorem. So or we can say that the total energy of the system remains constant. We can apply this theorem also. Work done by all the forces is equal to change in kinetic energy, or we can apply this, that the total energy of the system, total mechanical energy of the system remains constant. So what are the total energy? Let us assume that this is our reference level. So at this point, let us assume that A is our reference level and B is our equilibrium level. So at B, the potential energy would be minus mgx, because at A, potential energy is 0. So B is below, B is x distance below A. So the potential energy would be minus mgx. Similarly, the spring potential energy would be equal to half kx square and plus the kinetic energy. Kinetic energy would be equal to half mv square. And this is the energy at B. This is the minus mgx plus half kx square plus half mv square is the energy at B. And guys, tell me, what is the energy at A? At A, because this is the reference level, so there is no potential energy. And spring is in natural state, so there is no spring potential energy. And here the kinetic energy also is 0, so here is no kinetic energy at all. So this will be equal to 0 because its energy at A is 0. There is no gravitational potential energy, no potential, no spring potential energy, plus no kinetic energy. Okay, so we can write that x, we have calculated mg by k from this mg by k, so we can put here. So it will be minus mg into mg by k plus half k into mg by k square plus half mv square equal to 0. So it will become m square g square divided by k minus plus half m square g square divided by k plus half mv square equal to 0. We could have applied this also, that work done is equal to change in kinetic energy. Or we can apply the total mechanical energy at A and total mechanical energy at B is equal. So I have applied this. So it is coming out to be half mv square is equal to half m square g square divided by k. So half and half gets cancelled out. M and M also gets cancelled out. So V is coming out to be under root M into G by K. 1 M has got cancelled out, and so V is coming out to be M square under root mg by K. Mg square by K. So this is our V. Okay guys, so let us move to our next question. So let us now discuss what is power. Power is defined as the rate of doing work. Rate of doing work. What does it mean? That how fast the work is being done or how slow the work is being done. If the work is being done at a fast rate, work is being done very rapidly, then the power would be more. And if the work is done very slowly, then the power would be less. So we can calculate or we can quantify in this. The formula of this power is work upon time. We can say that power is equal to work upon time. So if t is equal to 1 second, what will be power? Power would be work done. So we can also define it in a way that in 1 second, the work that is being done is equal to power. In 1 second, the work that is being done is equal to power. So power is nothing but work done in 1 second. So this is what is power. Now there are two terms, average power and instantaneous power. Average power is nothing but total work done divided by total time. On instantaneous power, at some instant, at some particular instant, the power. So the formula of average power is work total upon T total, and the power of instantaneous power is formula is F into V. Okay. This term you will get to know in a bit detail. So this is the instantaneous power. It is representing the instantaneous power, dW by dt. It comes out to be F into V. Okay. So let us just do some questions, then you will more understand these terms, average power and instantaneous power. So let us just pick a question. It is given that a 60 kg student travels from first to fourth floor of a school at a height of 15 meter. What work did she do in climbing the stairs? So because weight of the person is mg, the force is mg, and it is climbing at a height of 15. So mg into distance, force into distance, that would be the work done. So it would 464 into 10 into 15, that would be the work done. And it is given that 240 watt of power is generating by the student. So we know that power formula of power is W upon T is equal to power. So here W is this much, 64 into 10 into 15, and we have to calculate time. We divide it by T and it will be 240. So here it coming out to be 4 6 24 16, and again 2 3s are 2 8, 3 5s are 15. So it is T is coming out to be 40 seconds. So like this we can calculate the formula. We can calculate time. Okay. Let us move to the next slide. Okay. So here you will get to know what is difference between average power and instantaneous power. So here it is given that the body of mass m is being pushed with the force F. You have to find the average power delivered by the force in time t and instantaneous power at time t. We know the formula of power instantaneous is F into V, and formula of power average is work total upon T total. So in this case, from the journey from 0 to time t, what is the total time? It is nothing but t. And what is the work done? Work done we can calculate. Let's suppose this is a mass m. It is moving by a force F. Let's suppose at time t it comes over here. And suppose at 0 it was here. It was at A, and when at time t, after time t, it comes at B. So, and the force is acting M. F force is acting. So here we can calculate the acceleration. Acceleration would be F by M, and we can calculate the distance. The distance is x equal to ut plus half at square plus half at square. And what is u? U is 0 because at is what initially at rest. So it will be half at square. And a is how much? We can know from this equation. A is equal to F by M. So it will be a half into F by M into t square. So it will be distance moved will be half upon 2m into t square. Okay guys, so this will be the distance, and we have to calculate the average power. So average power we have to calculate work done total and divide by time total. So what is work done? Force into distance, and what is distance? F into t square divided by 2m, and total time is t. So t and t gets cancelled out. So it is coming out to be F square t divided by 2m. So this is the formula of power. Okay, now so this is our average power. What is instantaneous power? Instantaneous power is V, F into V. So what is the velocity at this time? What is the velocity at this time? We can say that V equal to U plus AT. From this equation, we can say, and U is 0, and A is F by M into T. So this is our velocity. So from this, we can calculate instantaneous power. It will be F into F by M into T, which is coming out to be F square T divided by M. So we can check that instantaneous power is F square T divided by M, and average power is F square T divided by 2M. So at this instant, at B instant, the instantaneous power is more as compared to average power when it is calculated between A to B. Okay. So let us move with the next slide. Our last topic is commercial unit of energy. Actually, just see, there is unit of mass which is gram. So it is a very small unit as compared to kilogram. Similarly, joule is a very small unit of energy. So for calculating higher values of energy, we use a bigger unit, that is nothing but kilowatt hour. So that is a commercial unit of energy, kilowatt hour. Okay, guys. So let's let us just take or let us just see what is kilowatt hour in joule. So let us just calculate what is kilowatt hour in joule. We know 1 kilowatt hour. So what is 1 kilowatt? 1 kilowatt is 1000 watt. And what is hour? Hour we can convert as 3600 seconds. So it will be 3.6 into 10 to the power 6 watt into second. And what we know, that unit power is nothing but W upon time, and power's unit is watt, and the work unit is joule, and time unit is second. So from this we are getting joule is equal to, we just take it over here, joule equal to watt into second. So here the 1 kilowatt hour is coming out to be 3.6 into 10 to the power 6 watt second, and we have calculated that watt second is equal to joule. So it will be joule. So 1 kilowatt hour is 3.6 into 10 to the power 6 joules. Okay, guys, let us move to a question in this. It is given that a power station produces 2000 kilowatt in 30 minutes. What is the power output? So energy, power, we know that work upon time, and work is also whatever work be done, that is stored in energy. So work is given to be work is given to be 2000 kilowatt hour, because whatever work we do, that is stored into energy. So this can be work done as well as energy also. So here our work done is 2000 kilowatt hour, and time is 30 minutes. So let us convert. So what is the power output in kilowatt? We have to check. So power is given to be 200,000 kilowatt hour into hour. Hour and time is given as 30 minutes. So 30 minutes we know that 30 minutes is 0.5 hour. So hour and hour gets cancelled out. So it is coming out to be 0.510. So it is coming out to be 4000 kilowatt. So power is coming out to be 4000 kilowatt. So guys, let me tell you, the power of the formula of power is W upon T. And also, because work done is equivalent to energy, whatever work we do, that is stored in energy. So the formula of power can be energy of T, energy by T also. So okay, guys, so that's all for this video. Hope you enjoyed this video. Okay, thank you.